Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about few nanomaterial synthesis processes. In this lecture video, I will discuss about physical vapor deposition nanomaterial synthesis process. So let's get started. Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. In this lecture video, I will discuss about physical vapor deposition nanomaterial synthesis process, in which I will discuss first of all thermal evaporator, electron beam, magnetron sputtering, cathodic arc deposition, pulse laser deposition, and finally I will discuss about molecular beam epitaxy. First of all, let's try to understand what is physical vapor deposition, that is PVD process. As the name suggests, PVD is a technique that uses primarily physical means to deposit a thin layer of material. PVD involves a number of steps performed under high temperature vacuum conditions. PVD is characterized by a process in which the material goes from a condensed phase to a vapor phase and then back to thin film condensed phase. The most common PVD processes are sputtering and evaporation. Physical vapor deposition is used in the manufacture of items which require thin films for mechanical, optical, chemical, or electronic functions. First, a solid precursor material is gasified, typically through the use of high-power electricity or laser. The gasified atoms are then moved into a reacting chamber where the coating substrate is located. Source material atoms then stick to substrate, forming a thin coat. Physical vapor deposition is used as the deposition method to produce an extremely hard, corrosion-resistant coatings. Thin films made with PVD have a high temperature tolerance and superior ablation resistance. PVD is also considered an environmentally friendly process. The process does have few drawbacks. One of them main drawback is the high cost and the intense heating and cooling that is required. Physical vapor deposition is also a line of sight technique, which means it is not ideal for coating non-visible surfaces. The process is also considered to be relatively slow. Now let's see one analogy for physical vapor deposition. Let's consider a burning candle in which initially wax is in solid phase. Due to temperature of flame, it gets melt and converts into liquid phase. Furthermore, it turns into gaseous phase. If we hold any object like paper over the candle flame, then black pigment or lamp black gets deposited on it. In this process, wax is converted into the lamp black. Both have different phases and properties. Scientifically, heat from the flame melts the wax by radiation and conduction. Capillary action draws the wax up the wick. Molten wax is vaporized. Chemical reactions produce the flame. Heated solid carbon particles glow, sweeps away the products of combustion. Very similar technique is used in physical vapor deposition process. Physical vapor deposition involves the transfer of material on an atomic level, which has important benefits in several fields. The process flow diagram of PVD is shown here in block diagram, which includes a source generally called as precursor, which get sputtered evaporated into gaseous phase and then deposited onto the surface, which is again in solid phase. Here in this process, the physical morphology changes from precursor. In this process, the material that is going to be deposited onto a surface starts out in the solid form, gets broken down to the atomic level and deposited in the gas phase, and afterwards becomes a solid again. The atoms of the deposition material will react with the gas during the transport stage. Amongst any type of inorganic and a small range of organic materials can be applied via physical vapor deposition method. Now let's see the construction of physical vapor deposition system. In general, as shown in figure, the general mechanism and chamber of the PVD process. In the first step of physical vapor deposition, atoms are removed from the target material by using a very high energy ion source in the presence of a vacuum and an inert gas, usually argon gas. A high energy source is provided to the target material, so atoms are vaporized from the target surface. Then the vaporized atom moves towards the substrate surface and is placed in the chamber. The reaction occurs when the deposited material is a metal oxide, carbide or nitride, otherwise it will not occur. The vaporized atoms reach the substrate surface and are deposited there in the form of a thin layer. The physical vapor deposition process generates a uniform layer on the nanoscale to the visible scale on the substrate surface. This technique can be used to incorporate the layers of almost all inorganic materials and even some organic materials. Less resistance is induced in the PVD processes, so through heterogeneous nucleation, a tight layer formation occurs with improved mechanical properties like hardness and wear resistance. Now let's see few deposition techniques which are based on physical vapor deposition process. First of all, thermal evaporator. A thermal evaporator uses an electric resistance heater to melt the material and raise its vapor pressure to a useful range. This is done in a high vacuum, both to allow the vapor to reach the substrate without reacting with or scattering against other gas phase atoms in the chamber, and reduce the incorporation of impurities from the residual gas in the vacuum chamber. Thermal evaporation is the simplest way of depositing material onto a substrate. In this process, first important parameter is optimization. Purity of the film depends on the purity of the source material and the quality of the vacuum. Thickness of the film varies due to the geometry of the chamber. Collision with the residual gases aggravates no uniformity of the thickness. Next is limitations. Limited to low melting point metals, for example, aluminum, gold, nickel, chromium, etc. Dielectric material evaporation is difficult. Filament limits the amount of material that can be deposited. Density and adhesion is poor compared to the sputtered films. Step coverage is more difficult to improve. So these are the several limitations of thermal evaporator. What are advantages? It is simple and cheap, less substrate surface damage, and excellent purity of films. What are disadvantages? It is limited to low melting point metals. It's not possible to evaporate the dielectric materials. Filament limits and the amount of material that can be deposited. Density is poor. Adhesion is poor. Step coverage is more difficult to improve. So this is all about the optimization, limitations, advantages and disadvantages, as well as the construction of the thermal evaporator system. Now let's see next system, which is electron beam physical vapor deposition, that is Eb Pvd. Eb Pvd, target anode is bombarded with a electron beam given off by a charged tungsten filament under high vacuum as shown in this diagram. The electron beam causes atoms from the target to transform into the gaseous phase. These atoms then precipitate into solid form, coating everything in the vacuum chamber within line of sight with a thin layer of the anode material. So let's see the advantages of electron beam PVD. The deposition rate in this process can be as low as 1 nanometer per minute to as high as few micrometers per minute. The material utilization efficiency is high relative to other methods, and the process offers structural and morphological control of films. Due to the very high deposition rate, this process has potential industrial application for wear resistance and thermal barrier coatings in the aerospace industries, hard coatings for cutting and tool industries, and electronic and optical films for semiconductor industries and the thin film solar cell applications. So these are the advantages of Eb Pvd. Whereas the disadvantages of Eb Pvd are such as Eb Pvd is a line of sight deposition process when performed at a low enough pressure, roughly less than 10⁻⁴ torr. The traditional and rotational motion of the shaft helps for coating the outer surface of the complex geometries. But this process cannot be used to coat the inner surface of the complex geometries. The filament degradation in the electron gun results in a non-uniform evaporation rate. However, when vapor deposition is performed at pressure of roughly 10 raised to minus 4 torr or higher, significant scattering of the vapor clouds takes place, such that surfaces not inside of the source can be coated. Strictly speaking, the slow transition from the line of sight to scattered deposition is determined not only by pressure or mean free path, but also by source to substrate distance. So these are the several disadvantages of Eb Pvd. Now let's see another technique, that is magnetron sputtering deposition technique, which is also again a physical vapor deposition process. Magnetron sputtering is a deposition technology involving a gaseous plasma which is generated and confined to a space containing the material to be deposited, that is the target. The surface of the target is eroded or grind by high energy ions within the plasma, and the liberated atoms travel through the vacuum environment and deposit onto a substrate to form a thin film. In a typical sputtering deposition process, as shown in this figure, a chamber is first evacuated to high vacuum to minimize the partial pressures of all background gases and potential contaminants. After base pressure has been reached, the sputtering gas, which comprises the plasma, is flowed into the chamber and the total pressure is regulated, typically in the millitorr range, using a pressure control system. To initiate plasma generation, high voltage is applied between the cathode, commonly located directly behind the sputtering target, and the anode, commonly connected to the chamber as an electrical ground. Electrons which are present in the sputtering gas are accelerated away from the cathode, causing collisions with nearby atoms of sputtering gas. These collisions cause an electrostatic repulsion which knocks off electron from the sputtering gas atoms, causing ionization. The positive sputter gas atoms are now accelerated towards the negatively charged cathode, leading to high energy collisions with the surface of the target. Each of these collisions can cause atoms at the surface of the target to be ejected into the vacuum environment with enough kinetic energy to reach the surface of the substrate. In order to facilitate as many higher energy collisions as possible, leading to increasing deposition rates, the sputtering gas is typically chosen to be high molecular weight gas such as argon or xenon. If a reactive sputtering process is desired, gases such as oxygen or nitrogen can also be introduced to chamber during the film deposition. A magnetron sputtering source takes advantage of the phenomena which I just explained by using very strong magnets to confine the electrons in the plasma at or near the surface of the target. Confining the electrons not only leads to higher density plasma and increased deposition rates, but also prevents damage which would be caused by direct impact of these electrons with the substrate or growing film. Magnetron sputtering deposition does not require melting or evaporation of the source material, leading to many advantages over other PVD technologies. So first advantage is nearly all material can be deposited by magnetron sputtering regardless of their melting temperature. Second, sources can be scaled and can be positioned anywhere in the chamber based on the requirements of the substrate and the coating. And finally, films of alloys and compounds can be deposited while maintaining similar composition to that of the source material. So these are the very important advantages of magnetron sputtering technique. Here is a typical magnetron sputtering system on which I have done my PhD work of thin film solar cell deposition. Successful magnetron sputtering deposition requires the correct choice of power delivery system. Magnetron sputtering can be done in either DC or RF modes, but the former is more common. Metallic films like aluminum alloys, titanium, titanium tungsten, titanium nitride, tantalum, nickel, cobalt, gold, etc. can be deposited. Important reasons of sputtering are it uses large area targets which gives uniform thickness over the vapor or the substrate. It controls the thickness by deposition time and other parameters. It controls film properties such as step coverage, that is negative bias, gain structure, that is vapor temperature, etc. Sputter cleaned the surface in vacuum prior to deposition. So these are the important points in magnetron sputtering deposition technique. Now let's see another PVD technique, that is cathodic arc deposition. Cathodic arc deposition or arc PVD is a physical vapor deposition technique in which an electric arc is used to vaporize material from a cathode target. The vaporized material then condenses on a substrate, forming a thin film. The technique can be used to deposit metallic, ceramic, and composite films. The schematic of cathodic arc deposition and the pictures of the system are shown here. The arc evaporation process begins with the striking of a high current, low voltage arc on the surface of a cathode known as the target that gives rise to a small, usually a few micrometers wide, highly energetic emitting area known as cathode spot. The localized temperature at the cathode spot is extremely high, around 15,000 degrees Celsius, which results in a high velocity 10 kilometers per second jet of vaporized cathode material, leaving a crater behind on the cathode surface. The cathode spot is only active for a short period of time, and then it self-extinguishes and reignites in a new area close to previous crater. This behavior causes the apparent motion of the arc. As the arc is basically a current-carrying conductor, it can be influenced by the application of an electromagnetic field, which is in practice used to rapidly move the arc over the entire surface of the target, so that the total surface is eroded over time. Now let's see next pulse laser deposition, that is PLD-PVD. Pulse laser deposition is a physical vapor deposition technique where a high-powered pulse laser beam is focused inside a vacuum chamber to strike a target of the material that is to be deposited. This material is vaporized from the target in a plasma phase, which deposits it as a thin film on a substrate such as silicon vapor facing the target. This process can be occurred in ultra-high vacuum or in the presence of background gas such as oxygen, which is commonly used when depositing oxides to fully oxygenate the deposited films. A typical schematic diagram of pulse laser deposition is shown in this diagram, which shows PLD laser beam, which is NdArc laser, whereas CO2 laser beam also used for the deposition. The actual diagram of the system is shown at the right hand side, which shows substrate and plasma glow. Similarly, let's see three different schematics of pulse laser deposition. In figure A, schematic of pulse laser deposition setup is shown, in which the incoming laser beam is focused onto a target, thereby vaporizing the material of the surface region. The ejected material is partially ionized and forms the ablation glow, which is directed towards the substrate. In figure B, schematic of a RF plasma enhanced pulse laser deposition is shown, whereas in figure C, schematic of a gas glow setup combined with PLD, also known as pulse reactive crossed beam laser ablation. The two beams merge after passing the interaction zone and expand together. Under each schematic, a photograph shows the plasma glow for the corresponding pulse laser deposition technique. And finally, let's see molecular beam epitaxy physical vapor deposition technique. So what is epitaxy? Epitaxy is a method of depositing a monocrystalline film. Epitaxy, that is deposition and growth monocrystalline structure layers. Epitaxy is a Greek word which means epi means above and taxis means order, which is grown from gaseous or liquid precursors. In molecular beam epitaxy, substrates acts as a seed crystal, that is film follows that epitaxial growth result in a monocrystalline layers differing from deposition, which gives rise to polycrystalline and bulk structures. There are two types of molecular beam epitaxy. First is homoepitaxy, in which substrate and material of the same kind, for example silicon. And second one is heteroepitaxy, in which substrate and material are of different kinds, for example gallium and arsenic. Now let's see the epitaxial growth. As shown in this diagram, due to the interaction of molecular or atomic beams on a surface of a heated crystalline substrate, the solid source materials sublimate. They provide an angular distribution of atoms or molecules in a beam. The substrate is heated to the necessary temperature. The gaseous elements then condense on the vapor where they may react with each other. Atoms on a clean surface are free to move until finding correct position in the crystal lattice to bond. Growth occurs at the step edges formed, more binding forces at an edge. Now let's see important points of molecular beam epitaxy. Molecular beam epitaxy typically in a ultra high vacuum. Deposition rates are very low, that is 1 monolayer per second. Very well controlled, that is shuttering 0.1 second. Molecular beam epitaxy grows films with good crystal structure. It often used multiple sources to grow alloy films. Deposition rate is so low that substrate temperature doesn't need to be as high. It is very expensive but sophisticated system. A typical molecular beam epitaxy, that is Eb Pvd, is shown in this picture, which is installed in William R. Willey Environmental Molecular Sciences Laboratory. This is all about physical vapor deposition techniques. In my next lecture video, I will discuss about chemical vapor deposition techniques. So please don't miss my next lecture video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.